Hello, and welcome to Essential Skills for Physical Science. I'm Dr. Derek Fish, and I've been running the Science Centre at the University of Zululand for the past 30 years, and for most of that time running Matric workshops to help pupils and teachers like yourself. In this video, we're going to be looking at the 2023 November exam paper, the Paper 1 Physics paper. It would be very good for you to have a copy of this paper and actually to print it out and have it available. You can get this paper from the DBE website or from any of the Essential Skills resources. It can also be useful to have the marking guidelines or the memorandum, but that is not essential. I shall answer all the questions in this video. Remember, the memo has to have every possible answer, and you might actually find it more confusing than helpful. Finally, the memo only shows you the answer. It doesn't necessarily show you how to get there. And I'm going to be going through some really good strategies, some proven strategies of how to answer these questions. This is based on the Essential Skills resources, which were developed in 2020 and 2021 in a response to COVID, but are still in use and are being used by over 100,000 students in every province in South Africa. It would be really good if you could get a copy of this booklet, but for this particular video, all you need is the exam paper. And I really encourage you to try the exam paper. You should take 3 hours, try to answer it yourself before you look at my answers. We call this Essential Skills because facts fade, experiments expire, but skills stick. And that's what we're going to be focusing on. If you go to the book and go inside and look at the contents page looks like this. And it covers the various exam questions and gives you the video numbers. The idea is to use the book in conjunction with the videos. But for this particular video, again, video 10, all you need is the 2023 exam paper. Essential Skills is based on 4 skills, which I believe are essential for physics. The first one is graphs. And again, here's a comment from the National Examiner for 2023. It's right up to date. Having looked at all the national papers, the comment is that the interpretation of graphs or graphing skills is a challenge for many learners. So we look at 4 particular examples of graphs: motion, photoelectric effect, Ohm's law, and internal resistance. Then moving on, 3 other skills: free body diagrams. Again, the examiners comment that learners struggle to draw and label them correctly. Obviously, the biggest section is equations. Nearly 70% of your paper is solving equations. 2023 comment: learners still cannot work with scientific equations. And finally, multiple choice and ratio questions. Multiple choice was one of the weakest sections in 2023. And the comment that learners need practice apart from the exams. Now, this introduction to the exam is covered extensively in video 1.1 from page 4 in the booklet onwards. The basic structure of the exam hasn't changed since at least 2018. And although the questions change, it's really good to know the structure. If you're fully aware of it, you can skip the section. But if you aren't, you should watch carefully. So Paper 1 Physics is based on 4 sections. The largest is mechanics. Please note that it's a 3-year curriculum, and you need to remember your grade 10 and 11 work. Wave, sound, and light is a small section, and really the only thing that's examined is the Doppler effect and red shifts, which is always question 6 in the exam paper. Electricity and magnetism is the second biggest section, and it has 3 questions in the paper. And again, it's a 3-year curriculum. And then finally, matter and materials is a crossover section between physics and chemistry. And what you will find is question 10 on the photoelectric effect and spectra. Please don't forget grade 10 and 11 work. Again, here's a comment from the 2023 National Examiner. Lack of knowledge of topics taught in grades 10 and 11 could be seen in pupils' performance in question 7, that's electrostatics, and question 8, that's electric circuits. So you've done this a long time ago, so please make sure you recap that. Let's look at the basic structure of the exam. And again, this is covered extensively in video 1.1 on page 5. I will go through it quite quickly. It's a 150-mark exam with 3 hours. 3 hours is 180 minutes. So I recommend that you try to work at 1 minute per mark. Give yourself 10 minutes to read the paper at the beginning, 20 minutes to finish off at the end, That leaves you with 150 minutes for 150 marks. If it's a 10-mark question, allow yourself 10 minutes, no more. That'll make sure that you do finish the paper. There are 4 levels of questions, from recall to understanding, analyze to create. Recall questions, again, were very poorly answered. They should be 100% because they are just learning. But again, the 2023 examiner had this comment. Looking at the structure of the paper with the 4 sections, we blow it up a bit more. You'll see multiple choice questions are 10 questions worth 2 marks each. That's 20 marks. Average mark per question should be about 15. So you can see some are slightly more and some slightly less. And of course, it changes from year to year. 20 for multiple choice, round about 55 for the 4 mechanics questions, round about 13 for Doppler effect, 45 for electricity, and about 17 for photoelectric effect. And so you can see that every year the questions are the same. Obviously, the content of the questions will be different. What's perhaps more significant is to look at the average performance. This is the average pupil percentage per question. You can see it hovers around 50%. It's different every year, but you can see in 2023, the paper that we're going to look at now, multiple choice was very weak at 46%. That should be higher. The 2 electricity questions on electrostatics and circuits were low, and the lowest really was the photoelectric effect, and that has often been the lowest. So we'll look at that very carefully. You can get a far more detailed breakdown per section by looking at the diagnostic reports, which are also included with my essential skills resources, but we won't go into more detail here. Here's performance distribution curves in physical science paper 1 over the last 5 years up to 2023. You can see it really hasn't changed from year to year, and I think in a way it is adjusted so that the curves are matching. 30% is the pass mark. So you can see in 23, 76% of the pupils passed, which looks good, but that also means 24% of pupils failed to get 30%. If we make another line at 50%, we see that only 31% of pupils got more than 50%, and that means the majority, 45% of pupils, got a mark of between 30 and 50%, which really is very weak. So although 76% passed, 69% failed to get 50%. I want to say to you pupils and teachers, please don't aim for 30. That's just not enough for physical science, and especially if you plan to go into university. Aim for at least 50 and make sure that you're part of the 31% who get more than 50. And then just finally, looking at recall questions. I will not be covering recall questions in my videos because you don't need me for this. They are simply learning. You'll see that usually the first section of every long question is a 2-mark recall question, but adding up, that's 18 marks out of 150. And that is a significant percentage. Here's the average percentage that pupils got in 2023. It wasn't too bad, but it could be a lot higher. And with 2 marks, you should really state 2 important facts, and don't forget the key words and phrases. So let's have a look at question 1 from the November 2023 exam, which is always the multiple choice question. Now, from the exam introduction, you may have seen that the multiple choice questions were not particularly well answered in 2023. And you can see the average was 46% here. Here you can see the average question by question. Mostly the answers range between about 45 to 55%. That's across the whole country. I put those in blue. There were 2 questions which were well answered, 1.5, 1.6, above 60%. 1.4, the momentum question was very badly answered, 14%. We will look at that carefully. And then also 1.8 and 1.9, the 2 electricity questions were also badly answered. And photoelectric effect, not too well either. Now, if you look at my Essential Skills series, video 7 and page 66 in the book, deals with multiple choice. And multiple choice in some ways are difficult because you need to know all your work, all your topics, and it's very difficult to predict what sort of questions will come up. So they do test conceptual understanding, but here are some general tips which may help you. First of all, read the entire question. Don't jump to the answer before you finish reading the question. Secondly, try to answer it in your mind first before even looking at the answers A to D. This might help you being misled by the distractors. Thirdly, eliminate clearly wrong answers. And even if you're not sure of the right answer, you can at least have a better chance. Select the best answer. Even if you think one answer is not perfect, as long as it's the best answer from what's there. Remember, if there is, by chance, 2 correct answers, you will not be penalized for that. Fifthly, find the relevant equation from the data sheets. This is so important and is often the solution to many multiple choice questions. We'll talk about that more after this. Look out for keywords, not, sometimes, always, never. Know the difference between all of the above and none of the above. Never, ever leave it blank. If you really don't know what to do, close your eyes, take your pen, take a stab and guess, but always put an answer. There's no negative marking. Make an educated guess, and remember that the correct answer often contains more information, but not always. So number 5, find the relevant equations. You are given data sheets, but they are useless to you if you don't know them. Comment by the examiner: multiple choice is one of the weakest sections and learners need practice. So the data sheets. You are given 2 pages of data sheets. In my book, they're pages 38 and 39. The equations are very nicely arranged so that you can find them easily. But remember that you just see symbols, P equals mv. You need to know that P is momentum and is measured in kilogram meters per second, for example. So we start with the question 3, projectile motion equations. Then we have the question 2, Newton's laws equations. Question 4, momentum equations. Then we have question 5, work, energy, and power. Question 6, Doppler. Question 10, photoelectric effect. And then on the next page, 39, the electricity equations. Question 7, electrostatics. Question 8, circuits and internal resistance. And question 9, alternating current and electrodynamics. Now, there's also a constants sheet. Here are the questions in which these constants are often used. Of course, you don't need to know the constants. They're there for you, but you do need to know what they're used for. This data sheet is so important, not just in multiple choice, that in my book on page 40, I've got a little exercise to help you get to know your data sheet. I've suggested that either you can get a friend to ask you, or you can make a table like this. And once you've seen the symbol, for example, acceleration, you must know that the quantity represented there is acceleration, and the unit is meters per second squared. You must be able to identify every single symbol on the data sheet. And it can be confusing because V can stand for voltage and velocity and volume. So you need to know which version is being used in each place. There's also a special type of multiple choice question called ratio questions. I'll deal with these extensively in video 7 from page 66. And these are typically when you've got 2 bodies like the Earth and the Moon, with a force of gravity F between them. You're told that the bodies are moved twice as far apart and asked what is the new force in terms of F, and you must be able to do the sort of ratio questions. Again, if you want more about that, go to my video 7 on page 66. So all that you need is a copy of the 2023 November exam paper. You can get this off the DBE website or from my Essential Skills resources. There were 10 multiple choice questions. And as I said, they cover all of the work. The first 2 happen to be asked on Newton's laws, which is long question 2. 1.3 is asked on long question 3, projectile motion. 1.4, momentum. 1.5, work, energy, and power. 1.6, Doppler. 1.7, electrostatics. 1.8, electric circuits. 1.9, electrodynamics. And 1.10, photoelectric effect. So what's quite useful is just in this case, it's not always like this, but the 1 point number follows the number of the long question. So you can see, as I said, you need to know all the work, and quite often these are asked in quite unique ways. So you need the exam paper. It can be helpful to get the memo, but in this case, I don't think it is, because all the memo would show you is that. Now, it's good to know the correct answers, but if you don't know how to get to those answers, it's not going to help you particularly. So I think it's more important that you actually try these yourselves. And I'd encourage you to stop the video here for 20 minutes while you try to complete the 10 multiple choice questions and then go through my answers. Okay, so I hope you've taken the time to try these here. Let's go through them one by one. Again, I'm not just going to give you the correct answer, but hopefully explain to you how to get to that answer. 1.1 says a constant net force is applied to the block. Which one of the following statements is correct? Will it have constant velocity, acceleration, and so on? Now, the first thing is to go to our data sheets, the equations for force, and of course, Newton's second law, F net is equal to ma. If the force is constant, we know that the mass is constant, and therefore the acceleration will have to be constant. So the answer is B, a constant acceleration. That was quite well answered, 52% national average. Question 2 involves an object on an inclined plane. And again, there's lots about this in my book on page 33 and in video number 5. Remember, on an inclined plane, we have all these different forces when we draw the free body diagram. We're told the mass is stationary on the plane. If it's stationary, the forces perpendicular to the plane don't matter, but that means that the component of the weight parallel to plane must be equal and opposite to the friction, which is directed up the plane. So magnitude of the frictional force must be equal to the component of the weight. Don't worry about directions. We're just looking at magnitudes. 1.3 dealt with projectile motion. This was a little bit more tricky. You see the average of 46% in that it was an integrated question. It's asking you where the greatest change in kinetic energy will be. And kinetic energy usually comes up in question 5. There is our equation for kinetic energy. And because kinetic energy depends on v squared, the direction of velocity is not important because it will be squared. And we know that at point Q, the velocity is 0, and at point S, the velocity will be a maximum. Again, the direction doesn't matter. So we'll have 0 kinetic energy at the top. The ball has only potential energy there. Maximum kinetic energy at the bottom. So therefore, the greatest change in kinetic energy will be between Q and S. Question 1.4. This was a very difficult question, only 14% national average. So pupils were really confused here. And to be honest, this one is not easy. You're comparing the height from which a ball falls. That's really question 3, projectile motion, and you're comparing the momentum, which is question 4. So we need to pick up our momentum equation and also our projectile motion equation for the height. Now, putting them together, we know that momentum equals mv, and v is equal to the square root of 2ah, the height, because initial velocity is 0. So that tells us that momentum through velocity is going to depend on the square root of h. Now you're told instead of being dropped from height h, it's dropped from height half h. So the new momentum will depend on square root of half h. And taking the 2 out of the root side, that's 1 over root 2 times the square root of h. Remember, that was the original p. That's 1 over root 2 times p. And that is the answer. So that was a tricky one, and most people didn't get that right. But go through this again slowly and try to understand that relationship. 1.5 dealt with work, energy, and power. This was quite an easy question, and again, the average was high. Basically, you've got 4 forces acting on a box. Which ones actually do work on the box? Now, the box is moving on the horizontal surface, which means it only moves to the left and the right, not up and down. So we go to our data sheets, our work, energy, and power equations, take out the work equation. Also in my booklet on page 52, we define the fact that work is done when a force acts on an object and causes it to move in a direction parallel to the force. So the only forces which would move the block parallel to the force are Q and S. P and R are perpendicular, so they have no components in the direction of motion, whereas Q does have a component in the direction of motion. 1.6, Doppler, again, average was 63%. It was quite an easy question. A train making a noise moves towards a stationary listener. Which one of the following statements about the sound waves will be correct? On page 55 in my book and in video 6.6, there's this very nice animation. In this case, an ambulance siren is making a noise, and you've got listeners. And again, if we just allow it to come past again, you'll see that the pitch of the siren is 800 hertz. As it goes towards the listener, you can see he hears 820 hertz. When the listener is behind, it's 780. So the observed frequency is higher than the emitted frequency. 1.7 electrostatics. This was quite tricky and went back to some of the electrostatic definitions from grade 11, and clearly people had forgotten. But you've got a charged rod, a negatively charged rod, and two balls, Q and R. Q is repelled by the rod, and R is attracted. And you're looking at which are the possible combinations for the nature of the charges. Well, let's start with Q. If Q is repelled by a negative rod, the only possibility is that Q must be negative. Repulsion is only caused by like charges in each. So that means we can take out anything which has a different charge on Q, positive or neutral. Do you see how we are eliminating our distractors, which make it easier for us? We now only have two options left. But with R, there are two possibilities. R could be positively charged, which would cause it to be attracted. But you can see there's no option for positive charge. R could also be neutral, and it gets an induced charge. The negative charges in R get repelled to the far side, which leaves a net positive charge on the left, and that causes a neutral object to be attracted by a negatively charged rod. Now, you see we do have an option where R is neutral, and you can see by a process of elimination, we got to answer D. Question 1.8, electric circuits. Again, this was very badly answered, 32%. It is quite a difficult question, so we'll look at it quite carefully. 4 voltmeters are connected around the circuit. The question says, which voltmeters will have the same reading as V1 when the switch is open? Now, when the switch is open, no current flows. And remember, a voltmeter measures potential difference. So there will be a potential difference on either side of the battery, even with no current flowing, but not on either side of the resistor if no current flows through it, or the ammeter. What about on either side of the switch? Well, what we can see is that V3 is actually connected to the same 2 points in the circuit as V1, if we follow it the other way around. So V3 only will have the same reading as V1. Now, because this is a bit tricky, I've taken the wonderful simulation from PHET, the circuit construction kit, and can you see I've built the identical circuit here. Now, I'm just going to switch screen here, and we're going to go to the live circuit construction kit, where the voltmeter actually works. So you can see the switch is open. If I close the switch, then a current flows. And that would cause a potential difference across the resistor. But with the switch open, no current is flowing. Now let's check the voltage. Remember, it was 9 volts for the battery. So across the open switch, it is also 9 volts. But as I say, it connects round the other way. So you can see that that potential difference is the same as across the battery. If we move it, we can check across the ammeter, and that one is 0 volts. In fact, whether or not the current is flowing, that's 0 volts, because an ammeter has effectively 0 resistance. And if I switch it across the resistor, again, it's also 0 volts, because there's no potential difference because no current flows. Of course, if I close the switch, you can see we do get a potential difference, but the question asked with the switch open. So you can see what a great resource this is from PHET to actually test some of these for yourself. Back to our PowerPoint and question 1.9. This one was poorly answered. The average was 39%, and it was asking about a DC generator. Lots of pupils didn't pick that up from the split ring commutator here. Now, if you go to my booklet on page 62, we talk a lot about a DC generator, and this graph is shown, which can be voltage or current against time. Now, what you'll see from the graph is all the graph is above the line, so it's all positive. So the direction is constant, but the magnitude goes up and down, so the magnitude changes. So magnitude changes, direction is constant. So the answer has to be C. Finally, 1.10, also poorly answered. And this was not a difficult question. From the photoelectric effect, it asks about the ratio of the work function to the threshold frequency. So, of course, you need to go to your data sheets, pick up the equation for work function and threshold frequency. W naught, work function, equals HF naught, threshold frequency. If you take the ratio of work function to threshold frequency, it's simply H, which is Planck's constant. That really is quite easy, and it simply requires you to start with the correct equation. Now, the diagnostic report is a very useful document, and they had quite a few suggestions for improvement. Remember, this is written by the national examiner. Now, if you want to look at them in detail, you can pause the video on these 2 pages or get the diagnostic report, or I've done a very quick summary of the suggestions for you, and here it is. First of all, solve multiple choice questions by logical reasoning, not by lengthy calculations. Use generalizations and predictions. Secondly, ensure the data sheet is known really well. I can't stress that enough. Thirdly, practice multiple choice questions after each topic, not just in tests and exams. Solve multiple choice questions by eliminating the distractors, as you saw us doing. Incorporate MCQ into all lessons, especially for definitions. There are great apps you can use like ZipGrade or Kahoot, and also include the use of ICT. I've just shown you how useful PHET is, and there are others. And finally, use different sources to find multiple choice questions and practice them often. Some very useful MCQ skills from the national examiner. So remember, it's all about skills. This is the CAPS skills list from the CAPS document. And again, a comment from the examiner. Severe lack of skills is evident. Mathematical, conceptual understanding and integration of topics. Also free body diagrams, graphs, and equations. So that's the multiple choice questions. And we can go on from here to the longer questions. The list of the long questions is always question 2. Which deals with Newton's laws of motion, especially his second law, and possibly with gravitation. In 2023, it counted 16 marks, and the average percentage scored nationwide was 60%. So pupils did fairly well on this question. Now, the theory behind this is covered extensively in video 6.2 on page 42 of my book, and I encourage you to go there and take a look at that. Here you can see a snapshot of 3 recent exam papers, November 2018, 19, and 20. You can see that 2 of them have got a typical example of a falling mass piece with a string over a pulley, accelerating a mass piece on a table. 2019 was an inclined plane with 2 objects. 2021, again, an inclined plane with 1 object. And 23, what we're going to look at now, again, an inclined plane with 2 objects. So make sure that you understand inclined planes. And this is covered extensively in my videos and booklet. Now, I came up with this idea of an acronym called FEAR for handling question 2. And FEAR stands for the 4 parts into which question 2 is always divided: a free body diagram, an equation, an application question, and a recall question. There'll always be one of each of those. In November 2019, for example, the 17 marks were divided up by 4 for the free body diagram, 7, the biggest part, for solving the equation, usually Newton's second law, 4 for application, and 2 for the recall question. Now, the free body diagrams you can learn about from video 5. The equations you can learn about from video 6.1 and 6.2. The application, well, you really just need to understand the system. And the recall question is simply learning, so I won't deal with that here. Looking at November 21, similar breakup. And this question, November 2023, again, the national average for the question as a whole was 60%. People did very well in the free body diagram, and in the recall question, they did okay in the equation, but very poorly in the application question. Those are the average pupil marks for each section. Now, of course, it's always good to start with your data sheets. These are given to you for free in the exam. They're also at the end of the exam paper or in my booklet on page 38. And on the very first page, under force, we've got Newton's laws of motion. The Newton's second law, F equals ma, is obviously the most important one here. And then we've got the 2 for friction, static and kinetic, and the 2 for gravitation. Friction and gravitation did not come up in this question. So here's the question. And the first thing you see is there's a lot of reading, and it's quite good to use the diagram to display a lot of these things pictorially. Now, they give you the diagram, so you don't need to redraw it. You could perhaps just add an arrow to show that, as you're told, the blocks accelerate up the plane at 2 meters per second squared. I'd suggest that you choose up the plane as positive and down the plane as negative. So here again, you can see the 4 parts. The free body diagram is 2.2, which counts for 4 marks. The recall question 2.1, state Newton's second law. You must just learn that. The equation 2.3 for 7 marks. And the application question, which is 2.4 for 3 marks. We'll look at each of those in turn, except for the stating of Newton's second law. Let's start with the free body diagram. And again, I won't go into the theory. It's covered extensively in my video 5 and page 33 in the book. But start off with just drawing a dot or a circle for the body. Start with the obvious forces, which is weight acting vertically downwards, kinetic friction going down the slope to oppose the motion up the slope, the normal force always at right angles to the slope, and the tension force in the string, which is pulling up the slope. Now, of course, when we remove the diagram, that's what your free body diagram should look like. And here's how the 4 marks were allocated. 1 mark for label and arrow. The length of the arrows is not important. Any extra force, you would lose 1 mark, and the forces need to touch the body or you'd lose a mark. But really, you should be getting 4 out of 4 for that. Now, you might wonder why I dedicated a whole video to something which counts 4 marks. What you'll see is getting this free body diagram correct is essential to answering the next 2 sections. If you're unsure about forces on a slope, again, this is covered in video 5 on page 33. There's always a normal force at right angles to the slope, the weight vertically downwards, the force usually up or down the slope. And just remember that there are components of the weight. There's the component parallel to the plane, which is mg sine theta, and at 90 degrees opposing the normal force, which is mg cos theta. And we can take a copy of that triangle and fit it there. That angle theta is the same as the angle over there. So again, if you're unsure of this, go and look in my book. But let's have a look at question 2. And again, it starts off by considering the correct free body diagram. Now, please notice we are focusing on block A, so make sure you don't confuse with block B. And it says calculate the magnitude of the tension in the string. That string is only pulling block A, so only block A is relevant. So this is the equation. We're going to look at block A. The normal force is at right angles to the plane, so that's not important. And we only want to have forces up or down the plane. We have the tension and kinetic friction, so we're going to take the component of the weight which tends to pull the block down the plane, which is given like that. Now, that really helps us to put together our Newton's second law equation. So for the 4 kilogram mass, which is block A, we have F net equals ma, Newton's second law of motion from our data sheets. So tension is up the plane, friction and the component of weight parallel to plane are both down, so their negative is equal to ma. Now we know the mass and we know the acceleration, so now we can simply substitute in. 5.88 was given to us there in the question. We know the mass and we know the acceleration, and we can simply solve that, and we get a tension force of 36.6 newtons. Notice the question said calculate the magnitude, so we are not required to give a direction there, and that is 4 marks. Second question, calculate the magnitude of force F. Now, force F acts directly on block B, and again, it's easiest just to focus on block B and look at the different forces which are acting on block B. In this case, it includes a tension force pulling it down the plane. We get rid of the normal force, which is at right angles. We take the component of the weight, which is parallel to the plane. And we know from 2.3.1 that the tension in the string is 36.36 newtons. So we can now focus just on block B there. We set up our Newton's second law equation, F net equals ma for the 9 kilogram block. And we fill in the force, which is what we're looking for, minus the tension, minus the kinetic friction, minus the parallel component, and then fill in all the numbers. Notice the kinetic friction we get there for block B. Make sure you get the correct one. Fill in all the numbers and do a calculation, and we'll get that the force is 118.18 newtons. Obviously, it is up the plane, but we were only asked for the magnitude of the force, so we're not required to say that. So that's 3 marks. Actually, quite a tricky question for 3 marks with 4 different forces involved there. Now, onto the application question. And this is the one which was very badly answered and is not really that difficult for 3 marks. They tell you the angle the plane makes with the horizontal is now decreased. How will this change the kinetic frictional force acting on block A? And explain the answer. So we're looking at block A specifically. Well, it will increase the kinetic frictional force because if the plane becomes more horizontal, then basically the normal force will increase because the normal force is mg cos theta, and the frictional force is proportional to the normal force. You can just think practically, if you're pulling something across a horizontal surface, it'll have more friction than if you're pulling it down a slope like that. If you want to look at that more carefully, again on page 33, we look very carefully at the normal force on a slope, and you can see it's that component, mg cos theta over there, which comes into the friction equation. And as theta goes to 0, obviously cos theta goes to 1, and that force increases. So that was question 2 on Newton's laws. Right, the next of the long questions, questions 3, always deals with vertical projectile motion. And remember that it's only one-dimensional in the school syllabus. This was for 18 marks in November 2023, and the pupils did fairly well, getting an average of 56% for this. This question 3 is covered extensively in my videos in video 6.3 from page 48 onwards, and also in video 2 from page 8 onwards. If you look at the last few exam questions, we'll see that there was always something projected upwards. November 2019 and 20 both involved position time graphs. We can see in 2021, again, a balloon going upwards with an object firstly going up and then falling. And the one we'll look at now, November 2023, had a ball projected upwards and then bouncing on the ground, and a velocity time graph to follow with that. Now, of course, we always start with our data sheet, and we start right at the top of our data sheet on page 38 in the book or at the end of your exam, and we have 4 equations of motion. And this is what often causes confusion for pupils. Which equation do I use in which example? Now, there's 5 different variables: delta x, position, delta t, time, initial and final velocities, and accelerations. The way to choose your equation is not by looking at what is in the equation, but rather by what is not in the equation. And in fact, I introduce this table method in the booklet of actually checking at what variable is left out. And you'll see on page 48 in the book, it's covered extensively in video 6.3. Once you've filled in the given information, you can choose an equation very easily. We'll do it 2 or 3 times in this example, so you will see what to do here. So here's the question. Again, lots of writing, lots of information. They do give a diagram, and it's useful to start with that and to fill in other information. Also, just to be aware of which part of the flight you're looking at. There's the initial upward flight. Secondly, the downward flight from top to bounce. And thirdly, the flight from bounce to P. These are 3 separate sections. Notice also this is an integration question. They're asking you about kinetic energy, which technically is a question 5 issue, but it will be integrated into here. And pupils did find a problem with that. As usual, a 2-mark recall question, which I won't deal with. So let's start with using equations of motion to calculate the speed at which the ball was projected upwards. Now, the progress method, which I introduced for equations, says, first of all, draw a picture. We have that. Look at what is required. It says calculate the speed at which the ball was projected upwards. So that's the initial speed. What is obvious, for example, that the velocity was 0 at the top and that gravity is minus 9.8, and what is given to you. Now, choose a direction for positive. I would always say take up as positive. You can answer with down as positive, but I would suggest that you stick to this one here. So here's our table, and we filled in the information. 5.89 meters was given as the distance from the top of the building. And notice we're focusing on the flight from the building to the highest point, that dotted red line. The initial velocity is what we're looking for in 3.2. That's what's required. And then these two, the final velocity and acceleration, are both obvious. Now notice we know nothing about time for that part of the flight. So we choose an equation which doesn't have t or delta t in it, and that's equation number 2. So we take that equation and we simply substitute in what we know. Final velocity is 0. That was obvious. Acceleration minus 9.8 because it's down. Distance is 5.89, and we simply solve for initial velocity, and we get 10.74 meters per second is that initial velocity there. No need to give direction because it's just a speed that they asked for. Next, 3.3 says, after the collision with the ground, the ball leaves the ground with a speed of 11.92. That's a bit of given information, which I've put on the diagram there. They want you to calculate the amount of kinetic energy lost by the ball during the collision with the ground. Now, obviously, kinetic energy was lost because it fell from a much greater height than the height that it bounced back to. So obviously, in bouncing, in increase in temperature and sound energy, it lost some of that kinetic energy. Now, to calculate a difference in kinetic energy, we first need to find out at what speed did the ball hit the ground. So for this part of the flight, from the top to the bottom, we will look at the final velocity there. But notice we're focusing from the top to the ground, only that downward motion. So for that motion only, the total distance is 21.19, just adding 5.89 and 15.3. Initial velocity is 0. It starts from the top. G is minus 9.8. These are all the obvious things. And what is required by 3.3.1 initially is that final velocity. Now, again, we don't know the time, so we choose the same equation as before, put in everything and solve, and we get that the final downward velocity is 20.38 meters per second. Okay, it is negative because it's downward. Now, that final velocity will become the initial velocity for the bounce. And the final velocity after the bounce is 11.92. That was given in the question. The mass of the ball was also given as 0.5 kilograms. And we know that a difference in kinetic energy is simply the final kinetic energy minus the initial kinetic energy. And we can abbreviate the equation by saying it's half the mass times Vf squared, that's the red figure, minus Vi squared, that's the purple figure there. We put in the numbers. That was given Vf, the initial, we calculated in the first part of this, do the calculation, and we get delta Ek, or the kinetic energy lost, minus 68.31 joules. So again, that was an integration question, which required you to use an equation from question 5, the work, energy, and power section. And then finally, it says calculate the time taken for the ball to reach P after leaving the ground. So now we're focusing on this red dotted line from the bounce on the ground to P. We use our equations of motion in our table. We don't know the height of P, but we do know that the initial velocity was 11.92. That was given. We know that the final velocity will be 0. That's the highest point. A will be minus 9.8. And the time is what we're looking for this time in 3.3.2. So because we don't know position or distance there, we choose this equation number 3 because we don't need to know anything about y. You see how easy this table makes it to choose the correct equation. We put our equation there, we substitute in our values. 11.92 was given, 0 and minus 9.8 were obvious. Solve for delta t, and we get delta t equals 1.22 seconds. That's the time of flight from the ground to point P. Now, the second part of the question, they introduce a velocity time graph, not many marks, just 3 marks, and they want you to write down the numerical values indicated by point K, point L, and T2 minus T1. Now, because they're only 1 mark each, there can't be any calculation involved. So there's our original picture. There's the velocity time graph. Now, let me put in between, just to help us here, a position time graph, because this picture is almost a position time graph. And I want you to relate the points. So A is where the ball was initially thrown upwards, and that relates to point L on the velocity graph. Obviously, it has a positive upward velocity. B is the highest point, and that relates to point B on the velocity time graph, where the velocity is 0, because the ball is turning around. C is on the way down, so it has some negative velocity. D is where the ball bounces, and you can see that the velocity suddenly changes from a large negative to a large positive velocity as that ball bounces at point D. And P is the last highest point, and because it's the highest point, the velocity is naught at that time. So that enables us to relate these KL and T2 minus T1 to these points on our position time graph and here. Now, I'm just trying to explain this to you. Obviously, you don't need to do all of this in answering. If you need help with position, velocity, and acceleration time graphs, video 2 covers graphs of motion extensively, starting from page 8 in the books. I'll refer you to that. So let's answer the question. What's the numerical value for K? Well, K is on the velocity axis, so it's a velocity. It's the upward velocity after the bounce, so that velocity there. And that was given in 3.3 as 11.92. That was a given value. Secondly, L is the initial upward velocity over there, and you calculated that in 3.2 as 10.74 meters per second. You've previously calculated it, you just need to record it. T2 minus T1 is the time to reach point P from the ground, from there to there, and that is simply 1.22 seconds, which you calculated in 3.32. So that was question 3 on projectile motion. Question 4 always deals with momentum, usually has fewer marks than the other questions. In this case, it was 10 marks in 2023. And again, pupils did quite well with a national average of 57% for this question. This question is covered extensively in video 6.4 from page 49 in my Essential Skills series. Here's a snapshot of 2018, 19, and 20 questions, quite different. 2018 was an explosive force pushing a skater and a parcel apart. 2019, a bullet fired through a fixed wooden block. 2020, the usual two-body momentum problem. 2021, again, two bodies, but looking at energy. And the one we're going to look at now, 2023, a bullet fired, which lodges in a moving trolley, and they move together after the collision. So here is the question. Again, lots of information, and it's quite good to put as much of that information as possible into your diagram. And we'll go through the different bits as you go. You'll see we've got net force and time, and that's going to influence the equations we choose. But before we get to equations, 4.3, principle of conservation of linear momentum, is a recall question for you to learn. Write down the magnitude and direction of the average net force that the bullet exerts on the trolley. Now you see here, the average net force exerted by the trolley on the bullet is 591 newtons. So therefore, the bullet on the trolley is also 591 newtons, according to Newton's third law of motion, equal and opposite. And you do need to state that it's to the right or to the east, because, of course, the trolley was moving to the left, and after that force is exerted by the bullet, it moves to the right. Now, equations, again, the second part of the first data sheet page, page 38 in my book, deals with force, and with it is question 4, momentum. P equals mv, the definition of momentum, and your impulse equation here, F net delta t equals the change in momentum, which of course is mv final minus mv initial. Those are the equations we're going to use. Please make sure you know your data sheets well. So there's 2 questions, each for 4 marks. Calculate the magnitude of the velocity with which the bullet strikes the trolley, and of the combination of bullet trolley afterwards. So 4.2, we're looking for that information, and 4.4, we're looking for that information. Now, what do we know? Well, we know the mass of the bullet trolley combination. We can obviously add those two together. We know that the force is 591 newtons for 0.2 seconds. And we know that F delta t can give us the change in momentum, and that's a good starting point. Now, in fact, I think these questions have been wrongly ordered, because you actually need 4.4 to calculate 4.2. So I would suggest starting with 4.4, calculating the velocity of the bullet trolley combination, because we know what delta P is for that, because we know the initial velocity of the trolley. We don't know the initial velocity of the bullet. So we start with just the trolley. And remember, the impulse equation applies to single bodies, okay? It doesn't apply to multiple bodies like the conservation of momentum does. So we focus on just the trolley. And as we calculated, this is the force which the bullet will exert on the trolley for 0.02 seconds. So for the trolley, the single body, F delta T equals the change in momentum. So 591 is the force, delta T is 0.02. 2.7 is the mass of the trolley. We're just looking at the single body, times the final velocity minus the initial velocity, which is 3 in the other direction. That's why it's a negative. When we solve this, we get final velocity is 1.38 meters per second. 1 mark for the correct equation, 1 mark for substituting on the left, 1 mark for substituting on the right, and 1 mark for the final answer. Notice it asks for the magnitude of the velocity, so you don't need to give a direction, and we do know that it is to the right anyway. So going back to 4.2, we now know that the final velocity of the bullet trolley combination is 1.38 meters per second from 4.4. We know these masses. And we're now looking for the initial velocity of the bullet. And you'll see it makes much more sense to answer like this. So we're going to use our progress method. Remember, P is for picture. There is a picture, but we just add the final mass to it. What's required is VBI, the velocity of bullet before collision. It helps to focus on what we're looking for. What's obvious is there's no friction and momentum is conserved. Gravity is not important here. There's a whole lot of given information: mass of the bullet, mass of the trolley, mass of the combination, initial velocity of the trolley, and final velocity of the bullet trolley combination we calculated in 4.4. So we need to relate so that we can find the initial velocity of the bullet in terms of those given values above. The equation we use is that the sum of the momenta before are equal to the sum of momenta afterwards, or initial and final. So we can put together that little equation, and we're going to regard the bullet trolley as a single object afterwards. Substituting in, just taking those values and putting them in. Some you've calculated, some were given, and so on. And you solve for VBI, and we get an answer of 395.58 meters per second. To the right, again, it just asks for the magnitude, so we don't even need to say to the right. 4 marks, 1 for the momentum equation, 1 for substituting on the left-hand side, 1 for substituting on the right-hand side, and then 1 for the final answer there. So that was question 4, dealing with momentum. Question 5 deals with work, energy, and power. In 2023, it counted 14 marks, and there was a reasonable response, pupil scoring on average 54%. Now you can see over these 3 years, there was always an object going up or up and down a plane. So a combination of potential and kinetic energy, looking at mechanical energy. 2021 was pretty similar, object on a plane, inclined plane. 2023 was very different, and this is the one we're going to look at. It was on a flat surface, so there's no issues with potential energy. It's simply kinetic energy and friction. In this case, the trolley was pushed and came to rest under the force of friction after a certain distance, and some experimental data from a graph. So quite different, and a good one for us to look at. This is covered extensively in video 6.5 from page 52 in my Essential Skills series. Once again, lots of information. And before we get to the calculations, we're going to start 5.3, the work energy theorem. That's for you to learn the recall question. And 5.1 asks for the free body diagram, and then just to name the independent variable in the experiment 5.2. So let's deal with those. And notice free body diagrams always come up in question 2, but can come up in question 5, and sometimes even in question 7, electrostatics. These are covered extensively in video 5 from page 31. But again, we put a circle or a dot for the trolley. We start with the obvious force of the weight vertically downwards. We have the normal force at right angles to the surface, which in this case is flat, so it's equal and opposite to the weight. And then we have the force of kinetic friction, which opposes the motion. The trolley goes to the right, the kinetic friction goes to the left. Removing the diagram, 3 marks for 3 forces. And again, this is how the marks were awarded, and most pupils did fairly well with that. Now, the information is given in the form of a graph, and 5.2 says name the independent variable. That's always on the x-axis, and in this case, it's initial kinetic energy. So that was quite an easy start to this question. 5.4 caused a bit of problem. Calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. So again, we'll use our progress method to solve this, but first, the equations. Now, of course, work, energy, and power at the bottom of page 38, the first page of the data sheets, which can also be found at the end of your exam paper. So we're going to be looking at net force equals the change in kinetic energy, also the equation for work. And then because we're talking about friction, there's kinetic friction, and the normal force is also a weight. So net force is the change in kinetic energy. In this case, it's the work done against friction. And work is the force of friction times the displacement because of the angle between them. And that's the final minus the initial kinetic energy. Force of friction is just the coefficient of friction times the normal force. And the normal force is just mg. And all of this is going to enable us to get from kinetic energy all the way back to mass, which is what is asked for here. So in terms of our progress method, the picture is given. We don't really need to add any more to it. What's required is the mass of the trolley, or m. What's obvious is that the final kinetic energy is 0 because it comes to rest, and g is 9.8 meters per second squared. What's given here is the coefficient of kinetic friction. Now, the other information is given in the graph, which is quite different. And in fact, you can choose any of the pairs from the graph, or you can use the gradient. All of those are acceptable. I've just made it simple, choosing the first pair with initial kinetic energy is 6 joules, and displacement is 1.5 meters. So those become 2 pieces of given information in this question. So notice one of the skills required is to be able to read information off a given graph. Now we need to find m in terms of those given values, and it's a 2-step process. First of all, using the work done as the change in kinetic energy. So we substitute in the force of friction times 1.5, our displacement is equals to 0, the final kinetic energy, minus the initial kinetic energy, 6, we chose from the graph. So when you solve for the force of friction, we get 4 newtons. Now, we can also say the force of friction is given by the coefficient of friction times the normal force, and the normal force is just mg, and that enables us to say that this force of friction, which we solved, was 4, is equal to the coefficient, 0.18, that was given, times the mass times the acceleration of gravity. And solving in this equation, we get that the mass is 2.27 kilograms. Now, this was a 6-mark question. So how were the marks allocated? Starting with the equations. First of all, for equating the work formula with the difference in kinetic energy, and then substituting correctly on the left and the right. And then for getting the correct equation for the force of kinetic friction, substituting correctly into that, and finally coming up with the correct answer of mass is equal to 2.27 kilograms. So this is question 5 on work, energy, and power. Question 6 on the Doppler effect from the 2023 November paper. This one was for 12 marks and was actually the best answered in the paper, with the pupils' average being 62%. Doppler effect is covered extensively in video 6.6 from page 55 in my Essential Skills series. So looking at a few recent exam papers, you can see quite often the question is just a simple one of a vehicle moving and a stationary observer and just a change in pitch. November 2019 was very different and caused a lot of consternation. In that year, this was the worst answered question with 2 air pressure waves for the listener and the source. November 2020, another graph, in this case a step graph, of the frequency towards and frequency away. 2021 was a fairly standard ambulance siren, and 2023 the same again. And that's the one we're going to look at November 2023. So here's the question. An ambulance is moving away from a stationary listener with a constant velocity of 25 meters per second. And in this case, you're asked to calculate the speed of sound in air. Now you'll see in this wonderful animation here, 800 hertz is the fixed frequency of the siren. When it approaches, the listener hears a higher sound, and when it goes away, he hears a lower sound with a lower frequency. Now, there's just one Doppler effect equation, and it's on page 38 in your books, on the first page of the data sheets. And on page 55 in these booklets here, I spent quite a lot of time helping you to choose which one, because in fact, the single equation has actually 4 different equations, depending on how the pluses and minuses are used. So in November 2023, 6.1 says an ambulance is moving away from a stationary listener. So that's the third type here, with the source moving away from a stationary listener. And so that's the form of the Doppler effect equation. Velocity of the listener is 0. And also, of course, the frequency the listener hears will be less than the source frequency. So you need a plus at the bottom and a minus on top. And that gets us to this form. So here's our listener. Velocity is 0. Here's our source emitting the frequency, but the source does have a velocity. And we know that the frequency heard by the listener will be less than the frequency of the source. Remember, the Doppler effect is when a car goes past you really fast and you hear that. And this is the yaw part where you hear the lower frequency because of the relative motion. So this is really not too difficult. You've got your equation here. We just need to write down what is given. And we told the frequency of the listener, 512 hertz. We told the frequency of the source, 550. And you can see, as we predicted, that the listener here has a lower frequency than the source in this case. We know that the velocity of the source is 25 meters per second. So we simply need to take our equation, substitute in the frequency of the listener, frequency of the source, and the velocity of the source. V, of course, is the speed of sound in air. We know the velocity of listener is 0. We simply solve for that to get the speed of sound in air is 343.04 meters per second. Now, normally this is given as a constant, as about 330 meters per second. And so this should give you an idea that you're onto the right answer here. Not too difficult. 613, if the speed of the source increases to above 25 meters per second, how will it affect these 3? Now, first of all, the speed of sound in air remains the same unless the air conditions change, like temperature and pressure and so on. But for this case, it will remain the same. Frequency of the sound waves emitted by the siren remain the same because those are fixed. But the frequency of sound waves detected by the listener will decrease. And we know that because the velocity of the source is at the bottom of the equation, if that gets bigger, then the frequency detected by the listener will get smaller. Finally, a question about the redshift. Spectrum of a distant star when viewed from the Earth is redshifted. This is, of course, what happens in reality, and that's because all stars are moving away from each other because the universe is expanding after the Big Bang. And again, I don't have time now, but in video 6.6 on page 55, I do talk quite a lot about the redshift. How do we use the Doppler effect to explain the answer to that question? Well, a lower frequency, or you can say a longer wavelength, is detected, or the spectral lines are shifted to the red end of the spectrum. And that's how we know that it is moving away from in this case. So not too difficult. That was question 6 on the Doppler effect. Question 7 on electrostatics. In 2023, it counted for 14 marks. Wasn't a very difficult question, but was very badly answered. And the national average just 42%. Electrostatics is covered in video 6.7 and from page 58 in my Essential Skills series. Here's a snapshot of 3 exam questions, usually involving various charges and the interactions between them, either electrostatic forces or electric fields. You can see in 2018 and 2020, it was a 2-dimensional layout, so one had to use vectors to actually calculate forces or fields. 2021 was fairly straightforward, a linear arrangement, and again this time in 2023, linear arrangement of two charges and a point P. Just in this case, the distances were only given as variables. So here's the question: 2-point charges A and B, each 3 times 10 to the minus 9 coulombs, 3 nanocoulombs. They're stationary, and point P is basically 1/3 of the way between them. Describe an electric field, a recall question I'll leave for you to learn. Draw the resultant electric field pattern. This should be really easy. That's all you need to do. And the 3 marks are given as follows: correct direction of the lines away from the positive charges, 1 mark. Correct shape, bending away with no field in the middle, 1 mark. And no field lines crossing each other, and they must touch the charge. This was very badly answered, but should be easy marks. In my video 6.7, I use this fantastic simulation by PHET, which is called Charges and Fields. And you can see I've taken the exam question and set up a simulation of the electric field. The arrows show the field pattern, and that point charge there shows the size and direction of the electric field between the charges. It's pointing away from A simply because it is closer to A than it is to B. And I encourage you to spend some time looking at this great simulation. So data sheets on page 39, the second page of data sheets, there's a block on electrostatics. And in this case, we're only going to look at the electric field equations here. Very often Coulomb's law for the force between electrostatic charges is used, but we don't need it here at all. Don't be tempted to use it because it actually makes things more difficult. So those are the 2 equations we're going to be looking at. So 7.3, calculate the value of R. You're given that the electric field at point P is 27 newtons per coulomb. So your equation E equals KQ over R squared, the electric field at distance R from a point charge Q. Now, of course, there's 2 contributions to this. There's the electric field because of A, a distance R away, and electric field because of B, a distance 2R away. So these are the 2 expressions which you need. And of course, the net electric field will be EA minus EB. We know that EA will be larger because the distance is smaller, so we put that one first. And so net electric field of 27 newtons per coulomb is equal to the electric field at A minus the electric field at B. And when you work it all out, you get R is equal to 0.87 meters for 5 marks. Second part of the question says calculate the magnitude of the net electrostatic force that an electron would experience if it was placed at point P. Now, there's an easy way to do this and a hard way, and I suggest you do it the easy way. The easy way says we know the charge on the electron from our constant sheet, we know the electric field strength, and we have that F equals EQ. So this is a really easy calculation. 27 is the electric field strength, 1.6 times 10 to the minus 19 coulombs, the charge on an electron, and we can calculate that the force experienced by an electron at P would be 4.32 times 10 to the 18 newtons. They asked for the magnitude, so there's no need to give a direction. Now, of course, you could, as one option in the memo gives, use Coulomb's law to calculate the force due to A and the force due to B, and you can do a subtraction and get the net force. But please note, this question is worth 3 marks. That's the 3-mark answer. You don't need to do this much work. So always look for the simplest way to get to the answer. So that's question 7 on electrostatics. Question 8 on electric circuits and internal resistance. Up to 2018, this used to be 2 separate questions. Question 8 was in electric circuits, the grade 10 work. That's covered by my video 4.1, pages 20 to 25. And previously, question 9 was on the matric work on internal resistance, covered in my video 4.2 from page 26 onwards. Now they're together, and in 2023, this was worth 18 marks, and the marks were quite low for that. Pupils scored about 45%. Looking at a snapshot of some previous exams, 2018 and 19, there were graphs both times, but very different graphs. 2018 wasn't the typical voltage current graph you would expect for internal resistance. They flipped the axes and confused a lot of people. 2019, you have a step graph, the EMF of 13, and as soon as the switch is closed at T1, the lost volts and the terminal voltage drops to 10.5. From November 2020, and including 21 and 23, we've got a basic circuit analysis. Excuse me. So looking at our circuit here, it's a fairly straightforward circuit, 3 resistors, 1 light bulb, and they're rated just in terms of ohms to keep it simple. And 8.1 is the recall question, state Ohm's law in words. That's for you to learn. Now, particularly if you look back at my videos 4.1 and 4.2, what I've done is actually recreated the exam questions in terms of a PHET simulation. And you can see I've done it again here. And the PHET circuit simulation actually works. So you can see the ammeter actually reads a current of 1.5 amp. The ammeter on this branch of the circuit reads 0.75 amps. And we're going to see that those are correct. So that's a great way to understand things conceptually. And I'd encourage you to look at this particular PHET simulation of the circuit construction kit. Now, of course, we always need to go to our data sheets. Second page of data sheets, page 39 in my booklet. And for circuits, we need to know Ohm's law, R equals V over I. We need to know how to add resistors in series and in parallel. And we need the equation for the EMF related to the total resistance, external and internal. And finally, we need a power equation. There are 4. You can use any of them, but you will see that I squared R turns out to be the easiest in this 2023 question. So switch S is initially closed. So the circuit is as shown. Straightforward calculation of the total external resistance in the circuit. Now, this is just Ohm's law and series and parallel. You can see that we have 4 resistors, 3 resistors, R1 to 3, and a light bulb, which effectively is a resistor 2. R1 and R2 are in parallel. So the effective resistance of that total parallel branch is 10 over 2, which is 5 ohms. Those two are in series with RL, the light bulb. So 5 plus 10 is 15 ohms for this branch. And the bottom branch is also 15. And these 2 parallel branches with identical resistance, you can divide by 2. So the total external resistance is 7.5 ohms. Reading on the ammeter, remember from our simulation, this came up as 1.5 amps. Let's do the calculation. E equals I into R plus R. Simply substitute in. And remember that the external resistance we calculated in 8.2.1 to be 7.5 ohms. EMF is 12. We were given. Internal resistance is 0.5 ohms given. External 7.5 is a calculation from 8.2.1, and I is what we are looking for. Solving for I, we get I equals 1.5 amps, as was confirmed in that simulation. Finally, the power dissipated by resistor R3. Now, again, there are many power equations, but you know the resistance. You can easily calculate the current. And so we can say that the current through R3 is going to be half of the ammeter reading. How do we know that? Because both parallel branches have effectively a 15 ohm resistor in. So the current through R3 will be 0.75 amps, half of that 1.5 amps. We use power equals I squared R, which is 0.75 squared times 15, which is 8.44 watts. And that's the easiest way, using the previous calculations to get to the power. Now this what if question, what happens if switch S1 is open? Now effectively the circuit will now look like it does on the right. I've simply taken away the bottom branch because with an open switch it effectively doesn't exist, and R3 really is not in the circuit anymore. Now this question was very badly answered. So what will happen to the brightness of RL? Now it makes a difference here that you have an internal resistance. If there was no internal resistance, there would be no change. But in fact, the brightness increases slightly. Now, how do we understand that? We can do a calculation. We can say in the circuit we see here, we can solve for I and we get 0.77 amps. Now, previously, the current through the bulb was 0.75. So the current has increased, so the brightness increases. Or we could say the total resistance of the circuit has actually increased. It's now 15, whereas it was 7.5 before. And the total current in the whole circuit will decrease. So the lost volts decreases, I times small r, and the external volts increases, so there's more power to actually make that bulb shine brightly. If this is confusing you, let's take it a little bit more slowly. So here's the original circuit. Now in 8.2.1, we calculated that the total external resistance was 7.5 ohms. 8.2.2, that meant the reading on the ammeter was 1.5 amps. 8.2.3, that meant the current through R3 was half of that, or 0.75 amps. So obviously the current through resistors 1, 2, and the light bulb here is also going to be 0.75 amps. Now here's the new circuit with S open. This bottom branch effectively doesn't exist. And we calculated that the R external is now 15 ohms, not 7.5 like before. And when you do the calculation, as we did for the current through the light bulb, we get that it's 0.77 amps, which is higher than 0.75 amps as before. And that is why the bulb will actually burn brighter. So that is question 8 on electric circuits and internal resistance. Question 9 on electrodynamics. This deals with DC and AC motors and generators and alternating current. This is covered in video 6.9 and from page 62 in my Essential Skills series. And you should check that out because there's some great simulations there which will help you to understand. This is always a very easy question. It was 14 marks. Pupils didn't do wonderfully, but at least got an average of 54%. But I want to encourage you to try to finish the paper, at least to question 9. Question 10 is always much harder, but the marks on this are really easy, and I want to show you that. So looking at snapshot of 3 exams, there's always, first of all, a DC or AC motor or generator, and some very simple questions are asked about the components. Second half of the question deals with an alternating current calculation, either from a graph or just from some figures. 2021 was very similar. If you look at it, very similar to 2018. 2023 that we'll look at now was a DC motor and then a couple of very easy alternating current calculations. Let's get into them. So the simplified diagram of a DC electric motor, write down the name of component A. You can see that ring is split. So that is a split ring commutator. State the energy conversion that takes place. It's a motor. There's electrical energy in from the battery and mechanical or kinetic energy out, the opposite of a generator. What direction will the coil rotate? This is not quite so easy. That's why it's 2 marks. The answer is clockwise. And remember your left-hand motor rule. The blue is the magnetic field, which is from north to south. The red is the current, which is from positive to negative, because we're looking at positron flow, and that gives us black for the thrust. And it's very similar to this picture here. These are exactly the same, and basically the left-hand wire will be pushed upwards, the right-hand wire down, and the whole thing will rotate clockwise. 9.1.4, again, easy learning work. State 2 changes that can be made to the motor for the coil to rotate faster. And you can choose any 2 of increasing the strength of the magnet, increasing the current from the battery, increasing the area of the coil, or increasing the number of turns on the coil. Now, honestly, that was a very easy 6 marks. Second half, the alternating current calculation is not difficult. Define the term root mean square current. That's a recall question for your learning. But we go to our data sheets right at the end, page 39 in my book. It's always at the end of the exam paper. We have the equations for root mean square current and voltage, just the maximum divided by root 2, and then average power calculated in terms of those. These are given to you freely. So 922, switch S1 is closed, so effectively we're only looking at the top circuit with the kettle. Maximum current is 3.6 amps. Calculate the root mean square current. It doesn't get easier than this. Imax over root 2, which is 3.6 amps, given over root 2, which is 2.55 amps. 3 very easy marks. 923, equally easy. It says switch S1 is open and S2 is closed, so we're effectively using the red circuit here with the toaster in. The root mean square current is 2.62 amps. Remember, we were told that 220 volts was the root mean square voltage. Calculate the energy consumed by the toaster in 2 minutes. Now, these are power equations here, but of course, energy is just power times time. So work or energy is voltage times current times delta T. So our root mean square voltage, 220. Root mean square current is given 2.62. 2 minutes is 120 seconds. Multiply them out, and we get an answer of 69,168 joules, or you can give it as 6.92 times 10 to the 3 joules. I really want to encourage you to make sure that you answer question 9. It's one of the easiest questions, and there's some easy marks up for grabs there. So that was question 9 on electrodynamics. The last question from the November 2023 exam is question 10 on the photoelectric effect. And this counted 17 marks, which was quite a lot for this question, and was the worst answered question in the paper, national average being just 38% for this question. This is covered in my video 3, starting from page 17, my Essential Skills series. It's covered early in the series because I focus on the graphs. And you can see here in November 2020, this is the classic photoelectric effect graph of maximum kinetic energy versus frequency. Slope of the graph is h Planck's constant, and you can see it for different metals with different work functions. November 2019, they flipped the graph around. In 2021, they also use a flipped version of the graph. But 2023, no graph at all. In fact, 2 metal balls, and this is an integrated question where you had to use some knowledge of Coulomb's law of electrostatic attraction. So let's get into that. So here are the 2 balls. Again, the diagram, it helps us to add some features. We can note that A is negatively charged, B is not charged, A is free to move, and B is fixed in place. Excuse me. Ultraviolet light with a frequency of 2.8 times 10 to 16 hertz is shone on B. Ultraviolet light is very powerful, so as we can expect, it's going to knock some electrons off of B, leaving B positively charged, which will attract A. So that's what we're going to be working with. To find the work function of a metal is the recall question, which I will leave you to learn. Now, to understand the photoelectric effect, there's a fantastic simulation from PHET. It's freely available, and I talk about it extensively in my video 3 and on page 17 of my book. And if you're not fully understanding the photoelectric effect, I really encourage you to go back and have a look at that. For now, I just want to answer this question. So we always start with the data sheets, and at the bottom of page 38 in my book, the top of page 39, we have these equations for waves, and also, as I mentioned, for electrostatic. So we need E equals HF, the energy of a photon of light of frequency F, also E equals the work function plus maximum kinetic energy, where the work function is given by HF naught, F naught being the threshold frequency. But here we also need to know Coulomb's law, and we also need to know the number of electrons by dividing the total charge by the charge on one electron. So keep those all in mind. So the first part is quite simple. Explain using a suitable calculation why the ultraviolet light will eject electrons from its surface. So the question is really just, is the frequency higher than the threshold frequency? We don't know that. Or we can say how much energy is there, and is that higher than the work function? So that's the path that we're going to take. E equals HF, where H is Planck's constant, 6.63 times 10 to the minus 34. And the frequency 2.8 times 10 to the 16 is given. And that gives us an answer of 1.86 times 10 to the minus 17 joules. That's the energy of the ultraviolet light. Now, because that energy is greater than the work function, the electrons will be ejected. Now, I hope you know that 10 to the minus 17 is 100 times bigger than 10 to the minus 19. If you're not familiar with negative exponents, please make sure that you get on top of them before the exam. Second part, 10.1.3, sphere A carries a certain charge and requires a certain force to be moved. Now, they say calculate the minimum number of photons of ultraviolet light that must strike sphere B. Well, first of all, we want to calculate the charge on sphere B, and we're going to use Coulomb's law to do that. So straight Coulomb's law calculation. In this case, we know the force, it's given 0.027. We know the Coulomb constant K, 9 times 10 to the 9. We know the charge on A, 5.4 times 10 to the minus 6. The charge on B is what we're looking for, and we know the distance is 0.1 meters. So simple calculation gives us that the charge on ball B that's needed is 5.56 times 10 to the minus 9 coulombs. Now, how many electrons would need to depart B to leave a positive charge? And that we do from the calculation N equals Q over E. The total charge divided by the charge on one electron says it would be 3.47 times 10 to the 10 electrons. But the question said calculate the minimum number of photons. But remember that for one electron to be ejected, that will be caused by one photon of light. So therefore, the number of photons incident on the ball would be the same as the number of electrons ejected, which is 3.47 times 10 to the 10. Not really too difficult, but it starts from finding the correct equations. Now, the second part to this question, looking at spectra, and this often happens, and really this is learning work, obviously with understanding. In this case, a beam of white light is shone through a cold gas. Now, you should know that where there's a cold gas, it causes some absorption. So the emerging light is dispersed and a line spectrum is observed. Type of spectrum in this case would be an absorption or a line absorption spectrum. And to describe it, you would see a continuous spectrum of white light, like a rainbow, but there would be certain dark or black lines replacing specific frequencies, opposite of an emission spectrum. Now, because it's an absorption spectrum, when we look at 10.2.3 in these two diagrams, diagram A shows as the electrons fall from higher to lower energy levels, the energy is released. Diagram B, energy is absorbed in order to raise them up. And because we have an absorption spectrum, the answer is, in this case, diagram B. So that's the end of the November 2023 paper. I hope you found this useful. Remember that it's skills that are important because the questions change every year, but the skills stay the same. This table comes from page 5 in my booklet, but mostly it comes from the CAPS curriculum document. These are the skills which are required for physical science. And I promise you, these skills will take you right through university and will be valuable for life as well. And again, a comment from the examiner. It's a severe lack of skills which is evident more than knowledge. Mathematical skills, conceptual understanding, and integration of topics, also free body diagrams, graphs, and equations. And that's why I took the approach of the Essential Skills series. Thank you for watching this, and I hope it's been useful to you.